can't really call myself a Java programmer. I'm a C++ programmer with deep interest in multitasking. So when studying concurrency, I had to learn the Java memory model, and I know the C++ memory model reasonably well. So I'll give some examples in Java, but mostly this will be a more theoretical approach to concurrency in Java and the Java memory model. The thing is about Java memory model is that it is it's sort of the template for other memory models. That's why it's so interesting for a C++ program. C++ memory model came later and actually hasn't been implemented yet. It's just proposed standard C++ OX, which maybe will come up next year or 2 years. So this is my ambitious plan for today. I'll start with a motivating example. And then I will introduce the various notions, terms that are necessary to understand the Java memory model. So the example will show you where actually you need a memory model in order to understand your program, in order to write a program that works actually in a multi-core environment, multi-processor environment. So the notions that I will introduce is sequential consistency. And this is really a very simple thing. The trouble is that this is the way we always think about programs, sequentially consistently about programs. And it's really hard to wrap your brain around what can be an execution that's not sequentially consistent. Then I will talk about data races and the so-called DRF guarantee, which is the basis of the Java memory model. Data race-free programs behave sequentially consistently. They have sequentially consistent semantics. And then I will talk about a little more obscure corner of the Java memory model that maybe not everybody needs to know about it, but it's an interesting thing. I'll talk about causality and how causality could be broken during the execution of a multi-threaded program, meaning something from the future comes into the past and is used. And that leads to the second basic thing in the Java memory model. This is the out of thin air guarantee, that your multi-threaded program will not invent values out of thin air. I'll give an example of this. And if time permits, I'll talk about how these things can be implemented, how the compiler deals with the memory model, and how the JVM deals with the memory model. So there will be some details. So first of all, I would like to know more or less how theoretical I should be with this. How many people, for instance, know what is this out of thin air guarantee in Java? Has anybody heard of that? Oh, good. Sequential consistency. Okay. So this is more or less in the middle. Excellent. So without further ado, let me start with this example. This is some people say it's famous, some people say infamous example. It's called double check locking pattern. Okay, and for the moment, ignore this red word here. Okay. So what is the basis of this? I mean, does everybody know the double log checking pattern in depth? Why it doesn't work?
Yeah. Remind us why it doesn't work.
Okay. Well, first of all, so in a the purpose of this is it's called a singleton object. It means you want to have only one such object in your program. Okay. And the easiest way is just to initialize this object in your main, and you have this object, and everybody else can use it, share it, or whatever. Right? But it's only one object. Now, the singleton pattern is interesting when the object that you want to use is expensive. So the construction of this object might take a long time, or it might take a lot of resources. And your program might not even need this object in every execution. It might only be needed when the user clicks on a certain button or selects something from the menu. And in most cases, he doesn't or she doesn't. And all this work done up front will slow your program, will make it slower because of memory allocations and so on and so forth. So you might not want to initialize it for every single run of your program. So you want to lazily evaluate this object. As soon as somebody wants it, you initialize it, and then the next users will just use the cached value, right? So here's a singleton, then inside contains a foo object. Okay? And to get hold of this object, you call a method getFoo. Right? And this method checks, has it been initialized? No. Then let me construct it. And if it has been initialized, then I will just return it, whatever has been done. Okay? So this works perfectly well without any problems in a single-threaded program. Now, if you have a multi-threaded program, then of course multiple threads might be trying to initialize the object, and they collide, and they either allocate too many objects, and you don't have a singleton. You want to have a singleton, you want to have only one object per program, right? If multiple threads go there and race, and they all initialize an object, you will end up with multiple objects, and there will be no sharing between these threads. So the simple solution is, well, use a synchronized section, right? Take a lock, enter critical section, and that's it. So you do this synchronized, and you check for null, and if it's null, then you create, right? And that works perfectly. That's a great solution. Except that for some people this is not fast enough. So people started coming up with ideas. How can we optimize this? And of course, premature optimization is the source of all evil. In this case, it really was. But it was a good evil in the sense that it forced people to think more about memory models and what kind of guarantees a language has to provide in order for this thing to work. Okay, so the idea is this. Before I enter critical section, right, let me check foo. Okay, so this is outside of the synchronized section. Before I take an lock, this operation, this comparison is very cheap. Right? Taking a lock is expensive. Taking a lock, even with all the optimizations that modern Java has with thin locks and everything, it's still expensive. So let's do this outside of a lock. Do the check. Now, if the check tells me that it's null, well, then I should probably initialize, but I have to be careful because other threads might be initializing it as well. So this is an iffy case. But if the object is non-null, then I know it's already been initialized, right? I don't have to enter the critical section, I just return it immediately, right? So a quick check return, and in most cases, I have this short path without taking a long. However, if the object is null, then I enter critical section to initialize it. Because I don't want multiple threads to call new for the same object, for the same class, and shove it into foo. Right? So if multiple threads enter this, one of them will get into the critical section because it saw a null. Others that saw the null will block before entering. Only one thread can enter a critical section, right? So all the others will block and wait. Now the first one that entered successfully will initialize the object and exit. Then the next one wakes up, enters the critical section. Now if it just proceeded initializing the object, that would be bad, right? Because it's already been initialized. So it has to check again, but now inside the critical section. So there is no contention. It's either null or non-null. If it's null, you initialize. If it's non-null, you just exit and return the initialized null. And this second check, which is inside the critical section, that gives the name double-checked blocking pattern. Okay? So the first check is this shortcut, very fast. Okay? And that seems like perfect. I mean, if taking a log takes about 100 clock ticks on an x86, and comparing null pointer to null pointer probably takes 1 or 2 clocks. So that's a huge saving. It seems. But if you start analyzing, if you know a little bit about multiprocessing, things are getting a little bit iffy. Turns out that this wonderful code doesn't really work the way you think it would. And to see this, consider an object that is a non-trivial object. It has a constructor and it has data internally. So this object foo that I had on the previous slide, it's inside it has this public variable bar.
Okay, odd, but
So foo has bar inside, right? And in the constructor, it allocates this bar and calls the bar's constructor, right? So when you are calling new foo, what happens is that there are several things that happen. It's not an atomic operation. There are separate operations that are happening. 1, allocate memory, right? 2, call the constructor. The constructor internally allocates memory for bar and initializes this member variable bar. And then the next thing that happens, I didn't write it in order, and maybe I did it on purpose, subconsciously, because these things might not be executed in order. The final thing is initializing foo, the variable, the private member variable foo in the output. What is important is that 2 memory locations are initialized. Okay, this one bar, and the other one there was the output foo. Okay, I'm just going back to the previous slide. This one in this state, foo is initialized. Inside the constructor, bar is initialized. 2 memory writes to 2 different locations. Okay? Now, since these are 2 different locations, then both the compiler, the runtime, and the processor that use single-threaded logic might optimize this. I just say, you know, okay, this is the order the programmer wrote it, but I know better. I'll do them in a different order. Sometimes, not always, depending on how I feel. So what can go wrong in this? And still, let's forget about the volatile keyword, because that's the way to fix it. Okay? But without the keyword volatile, what can happen is that the write to foo and the write to bar are scheduled to go into memory. And then, before the first thread exits the critical section, another thread enters and says, get foo. Looks at the pointer, and so happens that the write to the point to foo has already been committed into memory. Right? So it sees foo, oh, it's known now. Let me skip the critical section and return the object.
Which has an empty bar.
Which has an empty bar because bar hasn't yet reached memory. It was rescheduled, either by the processor or by the compiler. There's no guarantee that things will execute exactly in the order that you wrote the program. Okay? And that's been true for a very long time, even on single processors. Things are executed out of order. But they always have, at least pretend, the processor pretends that they are in order. So if it makes any optimization, it makes sure that this optimization will not break the logic of the program, right? But this is not true about multi-threaded programs, yes?
You mentioned that it works fine with the volatile. I was under the impression that the reorder logic is only constrained by the synchronized block, not by the volatile reference.
It is actually. It is, yeah.
Volatile references also stop reordering?
They don't stop any reordering, but they are synchronizing actions.
No, they're pass-through cache actions. They're not synchronization actions.
Okay.
So
pass through cache, that's already talking about processor. Okay, so there are two views on this, and that's a good point. One is from the language point of view. When you are writing your program, you just see volatile, and volatile means synchronized. I'll explain this later, okay? From the processor point of view, that means clearing the cache, flushing the cache, stopping the rescheduling, blocking all the other processors so they have the opportunity to flush things, and so on. So there are complicated things happening in the process. That's the last part of my talk. So as you can see, you can get a null exception, even though this code looks perfectly fine. And why could it go wrong? Yes?
If you didn't do the check, if everything was within the synchronize, you wouldn't have this problem.
No.
It's just that you try to.
Exactly. Yes. It's because you are trying to access a shared variable outside of a critical section. Essentially.
Basically, within a synchronized block, your writes are visible even before you exit. That's what you're saying.
They might be visible to the outside world or might not be visible to the outside. They might be visible in different orders. However, if you only access this variable through the critical section, you have the guarantee that everybody will see the same picture.
But from within a critical section, you can do it right, and then everybody else will see it, even though they're not. They may see it or they may not.
Eventually, they will see that. That's for sure. Eventually, they will see. But if you do multiple writes, they might see it in different order. So, first of all, the processor can screw it up. And second of all, the compiler or the runtime. So how can the processor do that? Well, the designers of processors came up, sort of hit the wall as far as optimization goes. they hit the clock barrier, right? So it's very important for them to make very aggressive optimizations. And what was the most expensive thing that happened in programs was memory access. So memory is outside of the chip, right? First of all, there is a distance to memory that has to be traveled, even if it's traveled with the speed of light. That's still, fractions of nanosecond. Plus, if you have a multi-core machine, all the cores share the same bus. So there is contention when they are writing or reading. Some of them have to stop before they get. So memory access can take hundreds of clock ticks. So if there were no optimization, the processors would work like this. Do some very, very quick calculation, and then access memory and wait. You count to 100, to 200, nothing happens. Finally, something arises from memory, and you do very, very fast calculations. Sometimes even in fractions of clock. These chips are so fast, and the memory is so slow. It's like writing a program that has all the stuff in memory, and suddenly it has to go to disk, right? And blocks and waits. So in modern architectures, there is this on-chip logic, and the memory is like far, far away. It's the hard disk from the point of view of the process. So what they do caching, right? They bring a whole line from memory and cache it directly on chip. The access is very fast. Plus, in order to avoid contention, every core has its own cache, right? And there are multiple levels of cache and so on. So now the big headache is how to keep all these caches in sync, right? And they decided that in most programs, most of the time is spent in a single thread. Most memory accesses are not to shared variables. Most memory accesses are to local variables. So for these cases, you don't need all this logic of keeping cache coherency or flushing things to main memory and so on. So most processors, modern multi-core processors, just ignore the problem for most of the time, okay? And just do these optimizations if there were no other threads. These are called relaxed memory models for processors. And these processors can do things like reorder, reads and writes. They can delay writes or reads. They can even speculate. If there's a read in your program, they might just, since it takes a long time to get it from memory, they will just assume, well, I've seen this piece of code already 100 times, and it always been this value. So I'm just assume that this is the value and speculate. Okay? I mean, the logic on microprocessors is tremendous nowadays. They predict branches. They do branches in parallel. They remember what was the last value in this particular memory location, and so on. They have caches upon caches upon caches. But now, if the processor doesn't screw you, then the compiler or the runtime might screw you, because the compiler and the runtime might also have a relaxed memory model. And they might do these optimizations on their own. So it's a double whammy. And the reason, now, the double check locking pattern is supposed to work on the simplest processor, the x86. It also has a relaxed memory model, so it does some kind of optimizations, dangerous optimizations, but it has also a lot of guarantees about what things it won't do and so on. So on an x86, this pattern was supposed to work, except it didn't. And I know this from C++ because there was a huge discussion in C++ that DCLP does not work even on an x86. Turned out optimizing compilers were doing their own stuff.
You could add Java to that list. 'Cause it's the same thing.
Java, before the big memory model was announced, I don't know how many years ago it was, not so long ago. I think Java 2.0 introduced.
I thought double check locking didn't work until they changed the semantics in volatiles.
Yes. Isn't that 2.0?
My understanding was is they really had trouble on non-Intel hardware. Like it didn't work at all on Dell Alpha. But
Oh,
they
yes.
wanted to turn on optimizations that like
You need to speak to the crowd there, Jason. They can't hear you. No, seriously, let's say it to everyone if we're having a discussion.
The way I've heard it is that that it sort of worked on Intel. It didn't work on some of the other chips like the Alpha, but they wanted to do some of the same optimizations that the C++ people did, and they couldn't because it would really break it. So
And it's still-
Hotspot was essentially hamstrung because it couldn't.
It still doesn't work in C++. Because C++ does not have a formal memory model yet. It's only proposed. Java has a formal memory model. So that's a good thing. So in order to solve this problem, first you have to ask yourself the question, what do we want? How do we approach this problem at all, right? So we have to have a way in the language to tell the compiler, the bytecode compiler and the JVM, to suspend some optimizations. Okay? So this is one source of problems, is the compiler itself. Suspend some optimizations. Here, suspend some optimization. There has to be a way of expressing it, right? And there must be a way to tell the processor also that certain optimizations cannot be done. Okay? It turns out that all these processors that have relaxed memory models, they also have special instructions that tell the processor, excuse me, there's a break now, and all the writes, all the reads have to go into memory, and the world up to this point is fixed, and we can proceed. They're called memory fences, and there are also blocked instructions that serve a similar purpose. I'll talk more about it. I'm just sort of sketching this stuff right now. So these two requirements, from the language point of view, how to tell the compiler not to optimize and how to tell the processor not to optimize. And on top of this, we would like to be able to present this to the programmer in a way that does not involve assembly instructions and particular things related to processors. You know, I mean, on the alpha you should do this, on the x86 you do this, and if you use PowerPC, then it's yet a different way. Java is supposed to be portable between different platforms, so it has to have a way of abstracting all the stuff in some way, so that the programmer does not have to think about a particular process. And it has to be reasonably simple. And this simple view that can be the simplest possible view of looking at a program, of defining the semantics of a multi-threaded program, is called sequential consistency. That's the most natural model, and everybody understands this model. When I was reasoning about the double check locking pattern before I showed you how it doesn't work, I was using sequential consistency. I said this thing happens before this thing, right? The constructor of bar finishes before foo is initialized, right? Bar is initialized before foo is initialized. It seems sort of natural, right? Only if you know the nitty-gritty details of processors and the optimization that you find out that, hey, this is not really true. This does not execute sequentially. So the sequentially consistent model is simple and easy to understand, and we always use it when thinking about programs. So it's not a big deal. Okay? It's not some weird notion that theorists invent. And in a nutshell, you can describe sequential consistency as threads executing as if there was a single process. The good old times of preemptive multitasking. So one thread goes in, executes a bunch of code, then it's preempted, another thread comes, and it sees all the writes and all the modifications that the previous thread did. So during this context switch, sort of everything is flushed into memory, and the next thread starts. Okay, this changed. This thread changed the world, and now I see every change. So all these patterns, like through the double check locking pattern works if you have only a single process, unless your compiler does optimizations for you. So the simplest solution would be to say Java must guarantee sequential consistency. That's the memory model, okay? Memory model. Java guarantees sequential consistency. Unfortunately, this is not very realistic. For one reason. It's extremely inefficient. Because saying my program will have to execute sequentially consistently, every read and every write has to be sequentially consistent, you are essentially telling the processor, disable all these fancy optimizations. Forget about your caches. Read from memory, write to memory, no caching. Okay? That's a huge performance. It's hundreds of times slower. So the realistic approach is let the programmer specify which actions actually are crucial, which actions must be sequentially consistent, and the rest is single thread. Okay? The rest does not access shared variables. So only for the variables that are shared, we care. For variables that are not shared, the processor can do whatever it wants, and the optimizing compiler will do all its optimizations, and nobody will see any difference. So here's the more formal definition of sequential consistency. Maybe I'll just quickly go through this. So for each processor or each thread executes instructions in program order. So whatever program is written for this processor, for this thread, these instructions will be executed in this order. Now it's not really true, okay, because both compiler and processor do optimizations, but for single-threaded code, all these optimizations are invisible. Okay. So each thread executes instructions in program order. The problem is one thread looking at another. So instructions are performed by different processors. They can be arbitrarily interleaved. So this goes back to preemptive multitasking. So even though you have multiple processors here, multi-core, the result, if you impose sequential consistency, should be the same as if instructions from various threads were interleaved. So this thread does this, and then the next thread comes and does something else, and then the next thread, and so on. And there's a conceptual switch between the processor and the memory. And when a processor does a write, it first acquires a switch, writes to memory, and in this moment when it does this, no other processor can do a write or can do a read. So conceptually, this is a single switch between which always connect only one processor to memory, and then it flips to another processor. Each instruction is atomic and instantaneous with respect to other processors. So there's no way you chop an instruction in half and part of it is executed before the preemption and the second part after the preemption. Right? This is not really true for some instructions like string moves that on x86, but I think they are restartable or something. And the most important thing is that once you have this interleaving of multiple threads for a particular execution of your program. So your program executes and it does certain interleaving. Every time it's executed, it might do a completely different interleaving because it's a matter of timing, it's a matter of external outputs and so on. No two executions are the same. But for each execution, you have a particular interleaving in a sequentially consistent execution that is global. Every processor sees the same interleaving. Okay?
So it's not really arbitrary. You have to have rules about what interleavings are allowed, right?
In what context? I mean,
well, like the double locking problem, doesn't that introduce a constraint?
well, that's not really a constraint on the interleaving. It's a constraint of who sees what at what time.
But can't that be translated into a constraint on the interleaving?
Okay. If the double checked locking pattern is executed in a sequentially consistent manner, then there is no problem. Okay? And putting this word volatile actually forces sequentially consistent execution. Okay? Just this little word makes this whole thing sequentially consistent, and in a sequentially consistent execution, there is no way this pattern will break. But now I'm explaining what are the requirements of sequential execution, right? So the reality is that this is not how programs are executed, okay? This is an illusion. Java has to create this illusion that the program is executed sequentially consistent. Because behind the scenes there are all kinds of weird things happening. The processor does it, the compiler does it, right? But the programmer shouldn't be able to see this. For the programmer, this program executes sequentially consistently and everything works fine. So it has to sort of go against the processor, against the compiler, has to fix all these things. Now, as I said, enforcing sequential consistency for the whole program, for any program, is very expensive. So the solution is to guarantee sequential consistency only for a subset of programs, not all programs. not all possible programs that you can write in Java, you guarantee sequential consistency. You guarantee only for a subset. So for instance, this DCLP, if you write it without volatile, it will not execute in a sequentially consistent manner. It will actually be a bug in the program. So without this volatile, Java will execute it, but it won't execute it sequentially consistently. So this program without volatile belongs to the set of the to the subset of programs that are not going to be sequentially consistent. So we have to define the set of programs that will be executed in sequential consistency. And this set is called correctly synchronized program. So if you have a correctly synchronized program, its execution will be sequentially consistent. In order to know what a correctly synchronized program is, we have to know what are the non-correctly synchronized programs. And non-correctly synchronized programs are the ones that have data races. So I have to define what a data race is. Okay? A data race essentially is two threads are trying to do something at the same time to the same variable. Right? There's no synchronization. I mean, if both of them take a lock, then they'll serialize answers. But if they don't, they just race. You never know which one will execute first. And so this definition has two parts. One is to define a conflict. Conflict is not a bad thing. Conflict is an okay thing. It's just conflict is defined as two threads trying to access the same memory location, and at least one is a write. Because if both of them are reads, then it's okay to access them at the same time, because both of them will get the same result. Now, a conflict is not bad. What is bad is a data race. Data race is a conflict in which things are not ordered. Okay, so there is no synchronization between these actions. One way of synchronizing things is critical sections, the synchronized blocks, right? The other one that I will talk about is volatile access. And there is a more precise definition that uses the happens before relationship. It says things happen before this. If you can establish what happens before what, then you know if your synchronization is correct. So this is the first axiom of the Java memory model. A program that has no data races will be sequentially consistent, will have sequentially consistency. So if you can prove that in your program there are no data races, you're fine. You can reason about it in sequentially consistent manner. So if we can prove that the DCLP has no data races, it will work. Now, in order to prove that the program has no data races, how can you do that? It's not non-trivial thing, right? Especially if you have these keywords like volatile. Does it guarantee that there are no data races or not? In some cases, yes. In some cases, no. So the proof goes like this. And of course, nobody does it practically. But there's, at least theoretically, you can look at a program and prove that it's sequentially consistent. that there are no data races. Okay? And people write papers, PhDs, taking one particular algorithm and proving that it has no data races. All these lock-free algorithms. And this is so hard that actually there are publications, peer-reviewed publications on log-free algorithms that contain errors, and nobody saw them until many years later. So you start with all possible sequentially consistent executions. This is sort of a circular thing. In order to prove that something is sequentially consistent, you start with a sequential consistent execution, and if you don't find a problem with it, then it's sequentially consistent. But if you find a problem, then it's not. So for this program, you look at the synchronization, and you establish this happens before things. I'll show it on the next slide. And then you look for all possible conflicts, which essentially means look for all shared variables. Variables that are shared between threads. Okay, these are conflicts. And if these conflicts don't have a happens before arrow between them, then they are races. And the important thing to know about the happens before relationship is that when you have a piece of code that's executed on a single processor, the happens before relationship is just the order of the program. Right? So all instructions executed within a single thread, they are executed in this order. And if you see one instruction before another, this instruction happens before the other. The problem is when you have threads running in parallel, then the happens before relationship is defined by synchronization. And there are two types of synchronization. Now we are coming to this point. Okay? One type of synchronization is synchronized blocks, critical sections. So the actions are happen. So one thread takes a lock, releases a lock. Another thread takes a lock, releases a lock. In this particular execution, you can draw an arrow between the releasing of the lock by one thread and the taking of the lock by another thread. Okay? And this is only true in particular execution. So you can have another execution where these blocks are switched, right? And then the first one happens later than the second one, right? But for each possible execution, they are ordered one way or another. Okay? And the other synchronizing action is when you mark a variable as volatile. A read of a volatile variable, a write of a volatile variable happens before a read. Okay? And then again, depending on the particular interleaving, you might have write first and read next of the same variable. Then you draw an arrow from the write to the read. In another execution, they might be inverted. Then you draw an arrow from the read to the write, or don't draw an arrow.
So you're saying that a volatile does not generate a reorder barrier?
I'm not saying that.
It happens before relationship in some way. But
I'm talking about the model that a programmer has to have in mind when writing a Java program. Okay? Now, when you are talking about barriers and stuff, you're talking about the process. Okay? And the goal of the memory model is not to think about the process. Now, we know a little bit about processes, so we know what we could expect and what we should protect ourselves from.
Right, but it's also a compiler reorder barrier.
Yes, yes. Both the compiler have to collaborate on this and the process. Telling the compiler not to reorder these things is pretty easy because Java has control over the compiler. Java does not have control over what processors people come up with. Right? So this is the second part. Okay, maybe I shouldn't go into how much time do I have?
Another hour.
About another hour, a little bit less.
Another hour. Oh, okay.
If you want. Half an hour to
But,
an
but,
hour.
but how
if
much?
you want.
How much can you stand?
But there'll be questions.
Yeah.
Okay, so let me talk about this second part of the Java memory. So we established that data races are bad. If you have a data race, your program does not execute in a sequentially consistent manner, and in fact, all bets are off. Okay, so it's an incorrect program, and the results of this program are unpredictable. Java cannot tell you what the semantics of this program is. Yes?
So what happened to those arrows you were talking about? So what do you do with them then? How do you determine the meaning of those arrows?
Well, okay, so you have conflicts in the execution. So one thread writes something, another reads. Okay? This conflict becomes a race if there is no way of connecting these two with these arrows. Happens before arrows. This is a notion in simple terms. It's these two things are executed at the same time. You can't say which one was before, which one was after. They are just.
Until there's one that connects them. There's
If
nothing
there is
you can
something
say
that connects
about
them, yes, then you can say this one is first, this one is next, and the next one will see what the first one wrote. Right?
For example, the end of a synchronized block.
Yes.
Or the beginning of a synchronized block. Then you know that they line up there.
Exactly.
But without that, you don't know where they line up at. So you can have race conditions.
Right. And if your program protects all shared variables with synchronized blocks, you don't even have to know about this. Synchronized blocks just make your program.
So every time you go for a shared variable, you begin a synchronization. Yeah.
You should. Yeah. Essentially, you should.
That's one solution.
It's almost like single-threaded programming, though.
Yeah.
Except it's worse, 'cause you can get
except that you
deadlocked.
have to remember, every time you share any piece of data between threads, you have to identify what pieces of data you share between threads, and make sure you not only write it under a lock, but also read it under a lock. These two things have to happen. Okay? No access to shared variables outside of synchronized sections.
Now, how do these change with the new concurrency package? Because there you're not using synchronizing, right?
Inside they're using synchronized. It's just easier to use the objects.
I thought they're not using synchronizing.
Inside is the except in some dark corners of libraries.
Or where they don't have to, they don't tell you.
Stare not into the abyss.
I don't want to know about that. I'm just assuming they're doing the locks right inside those objects, inside those semaphores.
Except when they don't.
Well, so first of all, there is the programming for the rest of us.
Yeah.
This is just use synchronized sections for every shared access, and you'll be fine. Well, except you'll get into deadlocks.
Yeah.
But that's a completely different problem.
That's the next talk. Now they should
That's a
synchronize
series
everything.
of talks.
Those are for fee, right?
But the main purpose of the memory model is to define data races and avoid data races. So the simplest way of avoiding data races is use critical sections. Now, volatile variables should be used only in critical pieces of software. Pieces that you know are dragging your program down, your execution down. Because using volatile variables is equivalent to lock-free programming. It is lock-free programming, so you're not taking locks, right? This is lock-free programming, and if you want to write a data structure like a queue or a stack without using any locks, good luck. I mean, you either find it in peer-reviewed journals and just copy it from there after people wrote PhD theses. Okay. or don't do it at all. Or do it only in the very, very simplest case. I mean, this double checking lock pattern is so simple, so trivial. How can anybody fall into this? How can anybody design it wrong? And yet, programmers were using this pattern for the longest time, and they were surprised that it didn't work.
Because they focused on getting into the state, not getting out of it, right? It does prevent you from getting in, right? It's the fact that somebody is still in the bloody thing has not gotten out yet. That's what's not obvious to most people. I think you have to care about that.
I mean, a lot of people, when they first start concurrent programming, they understand that rights have to be protected. So when you're writing, you take a long. But it's really hard to explain to novices that every read also has to be protected. If there is a shared variable, the reads have to be protected as well. And this clever,
Assuming you don't mind stale values. And that's what
Assuming
the
you
dark
don't-
corners do.
assuming you don't need sequential consistency in your program,
Okay, yeah.
right?
That's the one example where it's actually a named sequential
So
consistency. I don't mind the last value. That's okay.
DCLP is so hard because there is a read which is done outside of a critical section. See, that's the special check that is done. It's outside of the critical section. So here is the cleverness of lock-free programming, lock-free reading. Okay, in such a simple pattern.
Maybe don't be clever and put the synchronized on your get instance
Yeah, and in fact,
and be done with it.
yeah.
And hold on to it. If you were going to do it 1,000 times, hold on to the darn thing.
Unless
Once you get it.
unless this is a critical bottleneck in your program. If this is a critical bottleneck, or if you write a library that thousands of programs will be using, then you might really sit on this thing, come up with clever ideas, ask other people, publish, write a PhD. Okay, so the simplest approach is to say programs that have data races don't have well-defined semantics. They can do whatever. We don't care. And this is the C++. Your program is incorrect. We can do whatever. We can reformat your code. Now in Java, we don't want this kind of behavior. Okay? The completely undefined semantics is bad. So even if your program is buggy, you still want your program to be reasonably safe, especially as far as security goes. You don't want to write a buggy program in general, right? But in particular, you don't want to write a buggy program that can be attacked by a malicious virus. And this kind of bugs that introduce data races are very hard to find, and most programs that do intense concurrency, they have these bugs.
How would someone exploit the data race?
I'll talk a little bit about it, not in great depth. So the second tenet of the Java memory model is we don't want Java to be vulnerable. Therefore, we have to close this loophole. And here's the loophole. Okay, how can program with data races do something really bad? Here's a very simple example. Very simple program. Thread 1, thread 2, 2 instructions each. there are two variables, x and y, that are shared between threads. And there are two variables, R1 and R2, which are not shared. They are local to this particular thread, and they are not shared. So initially, x and y are 0. So that's been initialized in the beginning of the program. And now thread 1 does the following thing. It reads x from shared memory and writes this value into y. Thread 2 reads y from memory and writes this value into x. Now, if there are two data races here, right? Data race on x. Here's a write, here's a read to the same variable. Okay? So that's a conflict. Since there are no synchronizing actions, it's a data race. And the same with y. So this is not a nice program. It's a buggy program, right? But if it weren't buggy, what do you think the values of R1 and R2 should be at the end? 0, right? Both should be 0.
Yeah.
Start with 0, move it around, it should be 0 when we're done.
Exactly, exactly. How can this value be 42?
Douglas Adams.
Incomplete writes.
Oh, I see. Okay. I was just gonna take a vote. I mean, who knows what 42 is? Do we have enough kids in this room?
But even with incomplete writes, you started with 0. You can't get anything other than 0.
Yeah, I mean, how can you get 42? Where would this 42 come from?
Yeah, half of a byte of a 0 is still a 0. So
Exactly.
or half of a word
Exactly.
or whatever.
Another
So,
thread.
actually, it is possible. It is possible. And you can maybe reproduce. I mean, it's unlikely that you get the value 42. but you can get any value out of thin air in this program. And it's a kind of self-fulfilling prophecy, you know? The processor says, okay, I have to read x, okay? So, memory, give me x, okay? Memory says, okay, just wait a few hundred cycles. And the processor says, okay, I don't have this time, right? I have to proceed in the meantime. So, let me assume, speculate, that x is 42. It's a speculation, right? Maybe because 42 was in one of the registers somewhere, or somewhere in the cache close by, or something. Or maybe in the previous iteration of some loop, that was the value. Okay? Because it remembers iterations of loops. It remembers what was, if this is a switch value or something, it remembers this stuff. They have long memory. So, I'll assume that it's 42. And eventually the stuff will come back from memory and I will check. Is that 42 or not? If it's not 42, then hey, I abandon all this speculation. Whatever happened because of the speculation will be unrolled. But for the time being, let me speculate. Okay, so R1 is 42. I write it into Y. Okay, and this is still speculative.
So if it's truly speculative, I can't write it to main memory.
No, obviously not. It goes into a cache, and it's marked as speculative. So everything that uses this value is also part of the speculation and can be unrolled. Okay? So thread 2 comes here, and it reads the value Y. And it reads the speculative value Y. And knows it's a speculation, right? So it doesn't take it seriously yet. Okay? So it reads 42 and writes it into X, still speculatively. And then after a while, the processor finally, the first processor sees it through this cache. It just percolates through this cache and sees the value of 42 and says, aha, I was correct. Bang, and turns out.
So you're saying, though, that for that to be the case, it never actually got to main memory?
No.
It's just through the
Not
cache.
But it had,
No, it's just through
you
the
can't
cache.
resolve the speculation without reading from main memory. So
No,
even
not
though,
really.
even though you
It
wrote a
can speculate
speculative.
through the cache. No.
What?
But doesn't it have to be a different process cache?
Well, there are several levels of caches.
But X when
there
it's
is a
written-
shared cache also.
Right, but when X is written in as speculative, it still hasn't resolved the original X value from main memory. Once it resolves it to
Yeah,
zero,
there's still a
all
read coming
things
back
become
from
out.
X, and then it'll.
No, this read coming for X, it does not have to come from main memory. It might come from a cache.
So
It's just postponed.
So the
why
thread
isn't
2 put a
X
value in
Thread
it.
one assumes that it will have to go from main memory and it will take a long time, so maybe it's better to do speculation, right? But this value can come from a cache.
But it's still speculative up until it becomes real.
Right, isn't the value of X in the cache, say, move R2, right, which came from a speculative value, so the tag goes along.
Okay, that would go into engineering problem. I don't know how the processor really implements it. I just know that this is possible.
At some point, it says, well, I have this tag, I'm gonna drop it now because it's been doing these cycles.
Yeah,
No,
yeah.
I think what happens is it drops the cycle because it sees a write into the cache memory for the X value, and it's not checking to see if it's a speculative write.
So-
So it assumes that that's what came out of memory.
Right. So it's not carrying the tag along. far
Well, the
enough.
tag is carried along, but the bit, the portion that sees the write for the X value doesn't actually check where it came from.
Okay.
Must be
Yeah,
calculated.
So effectively, they lose the cache.
Calculated.
Yeah.
But there has to be a point at
Yeah,
which
it's
the
because it's a processor
speculative
bug, I mean.
execution commits.
Yeah, we'll get on right.
Right.
And at this point, it's just a matter of checking consistency.
But this
Okay,
is,
and the
right.
consistency of all these speculative reads and writes says, this is fine, this works, I have proven.
So they're over optimizing a little bit here in the design of the processor essentially in order to limit how much they have to keep track of perhaps.
So I'll just mention that in the Wingding study group on concurrency, and when we studied the Goats book or Getz book.
Can't hear you 2 rows back.
I'm
Yeah.
sorry, the Wingding had a study group on concurrency, and we studied the Getz book. And he actually interacted with us through questionnaires and stuff like this. And the implication there was the only way to get an out of thin air value was in a partial write. There was none of this.
What process? Any process?
Correctly,
processor.
well, you're gonna,
You
suppose
could certainly
correctly
engineer a
written
processor with this behavior if you
What's
wanted
that?
to, right?
Yes, if you're running against a processor that can't keep track of speculation, then you're probably not going to get very far from
but
it.
isn't the point that unless, I mean, this speculation could happen, and unless you're synchronized, they
Right,
can't do
exactly.
it.
Yeah,
That's
they-
the point.
You can't
Is that-
depend on
That's
the
the point.
processor
Yeah, it can happen.
to be correct.
I mean, processors
Well,
are-
the-
Or the runtime.
The example that he brought to us was X equals 128 and Y equals 2, and the result is that X and Y are not
And-
128 and 2, there's some other combination
and they're-
muddled
and they're
between
long.
them. And they're long.
So therefore, there's not a common right.
And there's, so this example is a little bit weird, and we're sort of wondering, how's it gonna go anywhere but 0, because no matter what you write, you get zeros. But he had examples which were really half rights, and we're really gonna confuse things. So maybe 42 is not possible, but half and half of X and Y was more than possible all the time.
Actually, 42 is possible.
Wow.
It
That's
is possible.
another-
It is
on
possible.
Intel-
It has nothing to do with partial reads and partial writes. It's just a way speculations are dealt with. A speculation at some point becomes self-consistent
Yeah.
and is committed.
All the
It is
processors agree that it's
self-consistent.
42, so why do I have to check main memory?
It's kind of like garbage collection. Once you get something that's circular,
Yeah.
you
Yeah.
can't do anything about it.
Exactly.
Wow, that's only in.
Certain algorithms, and we're claiming there's better algorithms.
I can't really explain at the processor level how caches deal with this, especially that every processor has a different memory model, and it might be.
But the point is, we gotta say, flush, everybody who has a vote in this, get it out of there.
The point is that this actually happens, and this is an example that I haven't invented. This is an example from a peer-reviewed publication. Okay.
Do you have a bibliography?
I have at the end,
Okay.
but it's mostly, yeah. So this is the description of the speculation, how it finally validates, and we get the 42. Who knows who Fry is? Okay, so this is the guy who went back in time
Yeah.
and became his own.
Killed his grandfather.
Killed
You wrote a
his,
song on banjos?
He had an affair with his
Grandma.
grandma.
I'd say from people are
so this is what happened in this example. It was a self-validating causality loop, because the first thread predicted the value from the future. And based on this prediction of the future, it executed and it fulfilled the prediction. So Fry in the beginning was a virtual guy, right? He was the speculation of the universe, right? But eventually he went back in time and validated the speculation, and there he is. Now, why is this behavior so bad? Because it can lead to security leaks. Because instead of speculating the number 42, the thread might speculate the address, the handle of some other object that's in memory. And this particular thread should not have access to this. Could be a password. Okay? It
Or an
should
object
not.
that says true, can't access that other object. Oh, thank you. Yeah.
Exactly. Yeah.
You do a speculative Boolean somewhere.
A simple
Yeah.
permission Boolean would be really simple to screw up.
And the more we fiddle with our apps, the more we condense the big checks into 1 or 2 Boolean values that we're checking over and over again.
Exactly. And if it's a Boolean value, then 0 and 1 are natural speculation.
Well, that's
And in fact, the processor might execute both branches at the same time, speculatively, right? So if one of these branches leads to sort of self-fulfilling prophecy, there you go.
So Bartos, did the 42 have any correlation to the Hitchhiker's Guide to the Universe solution to the universe? It did?
Yes.
It did.
Exactly. Of course, this is the answer to a question that nobody remembers anymore. So, this is the second tenet of the Java memory model. No causality loops. Even if your program is buggy and has data races, we disallow causality loops. We disallow self-fulfilling prophecies. Now, how does Java do this? That's very, very tricky business, right? And here's the algorithm. That's a theoretical algorithm. I don't know if you want me to go through this or
Yes.
yes. Okay. So, so let's compare this to this other proof that the program is data race free. So in order to show that program is data race free, we start with all possible executions that are sequentially consistent. And if we find any of these executions in which there is a data race, we say it is not really sequential. Our initial assumption was wrong. If we don't, then our initial assumption was right, and the program executes in a sequentially consistent way. Now here we are dealing with programs that by definition are not sequentially consistent. They contain data races, real data races. So we cannot start with sequentially consistent execution because we won't see any of these weird speculations. Right? So we have to start with something that's not sequentially consistent. It's called well-behaved execution. So it's an interleaving, just like before, right? But it's not sequentially consistent, which means in a sequentially consistent execution, the read always gets a value of a previous write, right? That's sequential consistency, because they are ordered. So if you're asking, well, what value will this read return? Well, you look what happened before. Oh, before some other thread or the same thread wrote into this location, right? And it happened before. So here we are starting with something like this, but not all reads see the last write, because we don't know what the last write is. We don't have a definition of last write if this is not sequentially consistent. So we start with an execution that's very simple. It says it has data races, and all the reads are blind to data races. They will not see the value that is written in a data race. So it's sort of like data races don't exist. I'm only reading the variables that are sequentially consistently before me. So if there was a volatile write, I'll see the volatile read. We'll see that value. Even if in between there was a race that could have overwritten this value, I just ignore it. Okay? And then the procedure is, okay, looking at this, pick of this execution, pick a particular data race or a few data races at the same time. Okay? You pick a data race and you commit it one by one. Committing means you say this read have read something that happened before it. And there are two possibilities. Either it happened before it because of some synchronization, right? Or because it's in the same thread. Or it happened because there was another data race that has already been committed. So all the committed data races suddenly become visible. So it's an iterative process, right? You iterate. So you commit one data race, and then you restart the execution and see what values will be seen and what data races are remaining. Okay? Because if you have a data race on X, then you say, okay, the read of X will see some old value, the initial value, for instance, right? But since you are committing this data race, suddenly the write to X that was raised becomes visible. It's committed. So in the next iteration, some other read might see this write that has been committed. So you loop until you committed all data races. Okay? And if you go through this procedure, you are guaranteed that there will be no loops. Yes?
Is this intended as a thought experiment or as an actually implementable procedure to actually build into a JVM?
I think this is a sort of formalization of how things can be done.
Okay.
So this is a formal thing.
All right.
Now, if you are writing a compiler or a JVM, you just have to understand this procedure and see how you can implement it better. Okay?
Right, because
More
from
efficient.
a conceptual point, no problem. I just worry a little bit about that as a real implementation, like, you know,
Yeah.
production here. That seems a little weird. As a formal proof thing, I have no problem with it.
Okay, yeah. I don't really know how this thing is really implemented in JVM. I just know this formal implementation. So this is our previous example, but now we are executing it in a way that should break causality loops, and we'll see, is it really broken? So first we commit the race on X. Okay? There are two races. They are both invisible to read. So this read, since it's in a race with this write, cannot see this write. This read, since it's in a race with this one, it cannot see this write. So that's the first iteration. Now we take, let's say, this race and say, okay, we'll commit this race, okay? So what value is read here? You cannot see this one. You can only see the initial value of x, which is 0. So we have committed this data race, and we say, oh, this is the read. This read cannot see this right, so this read must see 0. And while we are committing this write will be committed. So now it's visible. But so happens that these data races here are completely separate. So the race on y, when you go to resolve the race on y, you have the same kind of thing. This read cannot see this write, therefore it must be 0. And you end up with both being 0. But since you are committing them one after another, you cannot see the value that will be in the future created by some race. You only see the values that are there, and then in the next iteration you will see the value that you committed. Right? But since you are committing them in order, you cannot be a loop.
How much does this slow you down? Is it like going back to a single-threaded program?
No. I think this
Well, so
it's definitely something that JVM is.
what they'll probably extract from this is some kind of formal equivalence between something that actually would work, like you're saying, right? Something that you could actually implement efficiently in a compiler. And this is essentially a model that you would like to prove some sort of formal equivalence between the actual thing you're doing and the full-on guarantee, right? You show this for somehow, right? The two are equivalent.
I think
This
what
one's just
happens
easier
is
to
that
understand.
the virtual machine is actually executing these multiple threads
Right.
and see what is happening. So it's executing some kind of execution. It's going through some kind of execution, and it knows the past. Right? It might store some information about last read, last write, and so on, or it can set a flag to itself. Okay, this is tricky. And then at some point when it sees, whoops, I've detected the data race.
Then it throws a fence in or something.
Yeah, then, well, either that or just, no, I won't speculate, okay?
We already know the trouble that gets into you.
I don't want to cause more trouble by speculating. Okay, so now the how this whole stuff is translated into what the processor does, right? Okay, this is the interesting implementation. So what we have to do is, I mean, logs are pretty simple, and in fact, logs might be implemented using volatile variables. Interesting. They are not, but the volatility is the key to this memory model. So how is volatile access translated into a processor memory model? So now we have a Java memory model, which is abstract, and then it executes on a particular processor. This is a concrete processor, and it has its own memory model. Every processor has its own memory model. Unfortunately, these two models are very different. Okay? In the Java memory model, you have a volatile variable. You have a location that requires synchronization. Every time you access this location that was declared as volatile, you have to do something special. Right? Processor does not understand this. Processor cannot say, okay, these particular locations in memory require special instructions to access them. And maybe in the future there will be processors that do that, or maybe not. I don't know. But right now, the processors can only separate multiple accesses. So you put a fence between two accesses. If the compiler puts a fence there, right, separating, let's say, read from write or write from read, the processor will do the right thing. That's a crude thing. I mean, you put a fence. It doesn't mean that the fence actually flushes stuff to memory. It's usually resolved within the cache, but it takes at least 100 cycles, even if there is no contention. So they are expensive.
So writing to a volatile is pretty darn expensive, like taking out a synchronized log. It's pretty much, it may look shorter in the code,
Well,
but
no. It depends on the process.
It
Okay?
may be easier, but it may not.
Maybe easier, maybe not.
Oh, okay.
On some processors, taking a log takes about the same time as writing to the volatile. But not all. And the most popular processor, the x86 processor, actually it's much cheaper.
To what?
To
Get a volatile and put in position.
read a volatile variable.
To read a volatile.
Yeah, because
Yeah.
sort of on the x86 all reads are there. In a sense.
There were a couple of releases of the JVM where synchronized was more expensive than volatile. Because they implemented volatile this way, and they didn't tell the guys who were responsible for the regular locks. So eventually they caught on and they used some of the same tricks. But yeah, Bill Pugh and Doug Leaf twiddled and twiddled and twiddled with locking models for like 4 or 5 years before Java Util concurrency came out with. And all of their stuff is based on volatile underneath now. There's no locks.
But you end up with some, at the assembly level, you end up with some of these same important instructions, but maybe fewer of them, so it goes faster.
Okay,
In
so
modern
let me
day,
explain. This is
yeah.
actually taken from Doug Lee's paper, the compiler construction tool, Java
Right.
compiler tool. Right. So these are the examples from there. So what the compiler does, there are these two stages. There is a compiler and there is JVM. Each of them has to play a certain role. The compiler produces byte code, right? So it doesn't know what processor it will be running. So it has to assume a certain, like the most conservative possible assumptions about the memory model of the underlying processor. So it has to translate these volatile accesses into memory values, right? And it doesn't know what memory values would use on a particular processor. So it assumes that it has to separate every volatile read from every volatile write using a banner. And there are 4 kinds of banners, depending on whether the first one is read, the second one is read, the first one is read, the second one is write, and so on. There are 4 types of these
So it
banners.
just says, here goes that combination, and here goes another combination. You work it out, BM. I don't know what you're gonna do. Okay.
Okay, so since it cannot really put barriers between accesses always, because it does not know what access was before and what access will be next. Will it be a read or will it be a write? It's not prescient. If it's within a single method, then okay, can do flow analysis and see, okay, this is a read, this is a write. I have to put a read-write back. Load store back. Store load store. Right? but in most cases it doesn't. Flow analysis doesn't go across procedure barriers. So there has to be a way of reconciling these two. Okay? The compiler sees in this program there is a volatile access. I don't see other accesses to the left or to the right or up and down, right? So I have to assume the worst. And the worst that it can assume is to put barriers around reads and put barriers around writes that will cover all possible cases. And it does it in such a way that reads should be cheaper than writes. Interesting. Okay? So these are the cookbook rules. Puts a store barrier before a volatile write. So it sort of protects it from a previous write. Puts a store load after every volatile write. So it protects it from the next read. Okay? But volatile reads are also instrumented. So together, they will always make sure that there is at least one barrier that fits this particular pattern between them. And this barrier could be on the right side, or it could be on the read side. But altogether, there will always be at least one barrier that fits the situation. Unfortunately, there may be more than what really is needed. Okay? So the second part of this load, and load store after every volatile read. So you can convince yourself that if you put these two barriers after every read, then it will be protected from a write that happens before it, and a write that happens after it, from a read that happens before it, and the read that happens after. They work together. Okay? Now the next step is the flow analysis. Compiler does flow analysis and says, okay, these barriers are not really necessary. It optimizes them away. If it can see what follows what in a particular flow, it can remove some barriers. They are redundant, unnecessary. And then, once the program is compiled, the JVM executes it. And it executes it on a particular process. Okay, JVMs are fit a particular process. So now it has to take these bytecodes, the barrier bytecode, and translate it into something. For instance, fences or lock instructions. And it so happens that on an x86, that's the processor that I know better than others. The x86 has also has a relaxed memory model, but it's not as relaxed as the Alpha. Okay, so it has certain guarantees, and if you take all these guarantees together, it turns out that the only barrier that is relevant is between write and read. That's one thing that's not guaranteed not to be optimized by the process.
So you're right, but he's still got it in the cache, so you have to say, careful, this value may be loaded soon, so do whatever you need to do, magic, so everybody will see the same value.
Right.
But only for that particular case.
Only for that particular case is needed. Otherwise, all other instructions on an x86, they sort of have built-in fences. They are more expensive because of that. That's why the x86 is not as fast as the Alpha, because it wants to provide this memory model that is actually what Intel did is they looked through lots of programs and they found what kind of patterns of access are most popular, and they designed the x86 multi-core, the x86 memory model around these patterns. So they wanted to make these patterns work, and yet do some optimizations that make it not a strict method.
So, I'm sorry, are you suggesting that on the x86 that all reads are eventually validated against the main memory?
No. No. Absolutely. Then that would be really extremely expensive.
So you...
No, this is at a cache level.
After volatile
Only if there
leave.
is a cache miss, then.
So, George, if you notice, there's nothing before a volatile lead, even in Doug Lee's overall abstract model.
I didn't understand.
I don't either, but he's claiming you don't need one.
In a lot of the
No,
processors.
because first of all, so consider two situations. There is a previous read, okay? This previous read has two barriers after it already, okay?
After. Yeah.
After it.
He got it there.
So it comes between these two. And if you have a previous write, the previous write has a barrier after it, which is a store load.
I don't understand how that process on one cache and processor affects another cache and processor.
Cache coherence. There are
On
very
most processors, there's a
complex
cross channel that
ways.
connects the two caches on the two processors.
Yeah.
So
One
they don't
processor can
communicate through
invalidate the
MME.
cache of another processor. They can mark them as stale values, or they can.
And store load has those consequences associated.
Yeah, it sends a cache invalidation to all the other processors.
Yeah, these caches are not totally isolated. They talk to each other.
You get two processors on the same chip.
Okay, so this is the final slide. Just a summary of Java memory model, because I said I introduced a lot of new terms and algorithms and so on. Here's the main thing. So one is this DRF guarantee. And if you have a program that has no data races, then it has sequentially consistent execution semantics. So if you don't have data races, and it's very easy to get rid of data races. Just first, identify all shared variables and lock them every time you access them. Every variable has to have a corresponding role.
Or stop sharing.
Or stop sharing. Yeah.
That's often the easier solution, is actually stop sharing.
Yeah, but the only things that you can stop sharing really is values. You can pass values between threads. And values are just built-in data types, like integers, right? You cannot pass objects between threads. It is automatically shared. And the second thing is data races don't break causality, and they don't come out with values. Honestly, these two things. Okay, and here's the resources. So the formal memory model is described in in the spec, in Java spec. I mean, if you look at the Java spec, it has a separate chapter on the memory model, and it goes through all these things, except that it does it more concisely, and if you don't know what the terms mean, it's hard to read. But after this talk, you should be able to read this. And this other thing is a paper about the memory model that just concentrated on this memory by Pew, and of course Doug Lee's compiler cookbook, which talks about these barriers and how they translate into fences. Questions?
Can you tell us a little bit about what's going on with C++? Did you say that this is being proposed basically in exactly the same implementation, or are there any differences?
Okay, the OX, C++ OX memory model has already been sketched and is publicly available, and it describes the C++ memory model. And it's a two-tier memory model. The default for most 99.9% of programmers, the the memory model is almost identical to Java memory model, so it guarantees sequential consistency if you don't have data races. Now, if you have data races, then C++ just gives up. Okay, it does not guarantee causality. Although I think there is a sentence in there that says it would be good if the implementation could actually prevent these things, but it's very non-committal way of describing it. But on top of this, there is this extremely complex memory model for non-sequentially consistent. And you can make a program that is not sequentially consistent, and you can have certain guarantees about it. So essentially, there is a way of defining volatile variable. It's not called volatile, although C++ has a volatile keyword, right? But it's a completely different. The direct translation of volatile from Java to C++ is atomic. And Java also has an atomic library.
Yeah, that's an object though, so that's.
So does C++'s atomic protect increments as well? Or not? Because volatile does not protect increments. You have to use atomic to protect increments in Java. Our atomic
Yes.
thing.
Yeah.
So is the which
Volatile
way did
is
they
not
go?
as strong as atomic.
Which do
Yeah.
they go with?
I mean,
full-on
otherwise
atomic?
Java would not need atomic.
Right. Yeah.
Yeah.
So
yeah. There are two parts:
C++ they went-
synchronization and atomicity.
Mhm.
Right? Java volatile does not guarantee atomicity.
But the C++ does.
C++ does.
Okay. Interesting.
What about how does D get around? Double lacking and sequential consistency?
D. Okay, he's asking this question because I work on the D programming language. And in fact, my task is to define a D memory model.
Call him next month.
And we definitely don't want to have as complex a memory model as C++. So it will be more Java. Nobody wants that. Yeah. And there are several people on the C++ committee that also said, no, we should have a sequentially consistent memory model. None of this crazy stuff that's so error-prone. But the fact is that there is the crazy stuff, and it's also atomic variables, but atomic variables have a default, which is sequential consistency. So you specify sequential consistency, there's enumeration. And if you don't specify
Get
anything,
an annotation.
no, it's an actual enumeration. Yeah. So it's like a constant. Predefined. No, library defined constant. So you define atomic variables, and then atomic variables have methods to access, like increment, read, write, get, set, whatever it's called. And with each of these methods, you can, if you want, specify the type of ordering. And the default is sequential consistency. So if you just don't specify anything, everything becomes sort of like volatile or like atomic in Java. Right? But you may specify, and you may say, well, this read is synchronized with other writes, but not other reads. Stuff like that. Or this particular read is totally free, unsynchronized with anything. So it's just like
one
a raw.
example I brought up where you don't mind old values, you just don't want inconsistent values. So
Right.
Values that never existed.
you don't want values that never existed, but you don't mind yesterday's value.
Right.
Just pretend you got there first.
But yeah, pretend you got there first. That's the way to put it.
Yeah. But of course, if you have this kind of access, you might see the values in different order than others.
Yeah.
Do you know what the world of Python Perl would be with those environments do?
I assume that
They
most
are-
languages use
they're all
sequential
lightweight.
consistency.
Well, they're all lightweight threaded, so they don't have cache erasure problems. One of the big problems with talk about the Python group is that they can't scale up because
They don't use the multi-cores.
right.
Okay.
But you use LAMP and you just start more and more Python instances, right? And everything's okay. So you just get two per processor and
Really
everything's fine.
large scale.
Yeah.
But the problem is how extensive is communication.
Yeah.
JMS. Yes.
So this paper is nearly 5 years old now, if I remember correctly, and it's built to run on processors that are 5 to 10 years old. Have Intel, AMD, these guys done anything for us in
Not
that
that I
15 years?
Not that I know.
Nothing?
Actually, they came out with memory models for these processors, sort of after the fact. In the beginning, there was a vague description of the memory model, just a few examples. This
So-
will work, this won't work, this will work, this won't work.
So
You have to
nothing
figure
new and fancy on Penryn or Nehalem or any of this stuff? Just still the same old stuff?
For the most part, the most popular processors, they're still the same. I don't know. The alpha is also an old processor. But the alpha has a good performance because of this very relaxed memory.
Nobody makes alpha, right? Alphas are long speeds.
Question here? Yeah, I've just sort of a banal programming question, if that's all right.
Okay.
Going back to your...
But I'm not a Java programmer.
No, that's fine, but I think this is actually specific to what you talked about and the double check synchronized example, actually. If in that original programming example we stripped away the synchronization so that we had just a bare null check, the initialization of the variable and then the return of the reference, but replace the initialization with the initialization of a local variable, and then assigned the value of the private instance variable to the initialized local variable.
Yeah, and a temporary variable.
Is that sufficient to get, so that still doesn't get you out of the situation of having unprotected access to the...
It doesn't.
Huh.
It doesn't. You just have more rights there. Okay?
Well-
and these 3 rights, okay, or 4 rights can also be real.
So that means that, say that you interposed like a method call on your local variable in between the initialization of the local variable and the assignment to the instance variable. Do you understand what I'm saying?
Yeah, I
I mean,
understand.
that method call has to be made,
Mhm.
like, the caller of that method doesn't have to
Well,
worry about some other thread initializing.
let me read.
have to be called.
You're just trying to
It
slow
can be
things
in
down.
there.
No,
It doesn't
let-
guarantee. it's not
No.
guaranteed.
I'm not trying to slow anything down. I'm trying to eliminate locking and still provide, I'm trying to think of
Any method can be inlined and then reordered.
This is a very good question. What it boils down to is, can I somehow fence this access that happens
Application
inside
level.
the critical section, right?
Correct.
I do something in there that makes the read that's outside suddenly see
and
things correctly.
And I was thinking that, when you said that if your program only operates on local state, right, if all of your threads only operate on local variables, then we're guaranteed to have a model where everything is kind of sequentially consistent because you couldn't prove otherwise, right?
Right.
So, I was wondering if the use of local variables had to preclude some of that scheduling magic. Where the initialization inside the local variable could be,
But you still have
scheduled
these
somewhere
shared
else.
variables. whether you want to-
More than the local variables.
I mean,
are
because you
shared.
want to share the same instance
Keeps
between
you out of it.
multiple threads.
Right.
I mean, if you can have an instance per thread, then fine, there's no problem.
Sure, but I mean,
You want to share it.
But from my previous example where I said, interpose a method call, I wasn't suggesting that the method call would slow things down so that we had enough time to finish.
The thing is, if it's isomorphic to the first thing, right? If it's something that the compiler can look at and say, well, all this extra stuff here doesn't really do anything. Therefore, I'm just going to optimize it away, you end up with the same situation, or could end up with the same situation, and then you're back up to pre.
But there's actually a
If it
deeper
doesn't
point
see a
of this.
provable data hazard, it can reorder in any order it wants.
Yeah, I guess and I guess maybe the ideas of what the compiler can recognize are a little abstract.
You don't want to get in that game.
Yeah, you don't want to
That's not a winning.
Well, I don't, and I guess I guess I was kind of thinking that like you can't. I'm kind of surprised to think that the compiler could see that I've constructed a local variable, would be smart enough to recognize that I haven't done anything that references internal state in that object, such that it could schedule the initialization of it could schedule the logic of that constructor somewhere else.
Yeah, but you're still in your Java code trying to do something artificial to get the compiler to do something.
Sure.
Well, let me give you an answer that will actually resolve this problem. It has nothing to do with the compiler. It has everything to do with the processor. Because essentially what you are saying, can I make a modification inside this critical section that would fix it?
I want to, basically
Right? I mean, you are saying a method call inside the critical section. Or maybe you can say, like, put a write barrier after this write, okay? And that's it, right? Put a write barrier.
Right.
Yeah. Why doesn't that work? It's a simple solution. The answer is no, it doesn't work. It doesn't work. You cannot. Barriers have to rendezvous. There has to be a corresponding barrier before the read in order to see the barrier after the write. Okay? So the reading has to be protected too. That's a very unnatural thing that happens.
Right.
But
Write barrier is just
write
part.
barrier is just like, one leg. There has to be another leg on the read side so that they communicate.
So what if you get some kind of transactional memory? Would that solve this problem?
What? Transactional memory. Yes, it would solve this problem, but at what cost?
Here's the box containing all the other problems you've got. Good luck.
There's a nice paper actually in ACMQ a couple of months ago where some IBM guys spent like a couple of years trying to make software transactional memory work and looking specifically at the performance issues that come out of that. And the answer is that in the general case, it's hard to make it work without spending a lot. It's expensive to do type systems.
Oh, yeah.
Oh, okay, folks. I think we're running a little over our time here. Thanks for the great talk, Bartosz. And if you guys want to continue the discussions, we usually meet for drinks at the Virginia Inn down the street. It's on the corner of Lenora, I think.
Hopefully there'll be seats today.
And first, hopefully there'll be seats to St. Patrick's Day.
Is it an Irish pub?
Any pub is an Irish pub.
Well, at least it's not even themed.